this is your friendly neighborhood physics teacher here, and we're going to talk about energy. So this is your energy review for your test coming up. So we're just going to go through the problems. Here we go. So number 1, you are riding your skateboard to class. You push off the ground and coast. Why do you slow down if energy is conserved? So basically what energy is conserved means that the energy you put in is the energy you get out. But in this case, when you're on the ground with your lovely skateboard here, your wheels and the ground are touching. So that's causing friction and causing basically work due to friction. And so that friction is slowing you down. So that friction is why it slows down. So why do you slow down if energy is conserved? It's because friction is taking that energy away. Number 2, a crane can lift a 500 kilogram mass to a height of 30 meters in 2 minutes. What is the work done by the crane? Okay, so the first thing we do is write down our givens. So givens, we are given a mass of 50 kilograms. The reason I knew that was a mass is because of the kilograms, and plus it said it. Height is y equals 30 meters, and t is time to minutes. Our unknown, what we're looking for, we are looking for work. Work is always in joules. So the equation we have is work equals force times distance. So we know that work equation. And there's a given that we always have that we forgot to mention. So we know that our acceleration due to gravity is 9.8 meters per second squared. And specifically, this is the force of gravity. Remember, your force of gravity is just mass times acceleration due to gravity. So we can take that, plug that in, and so we get that work equals mass times acceleration due to gravity times our distance. Well, in this case, our distance would be our height. So that's just basically our work equals our potential energy, because it's gaining potential energy as it goes up. So now we just substitute. So we're looking for work. The mass is 500. We know acceleration to gravity is 9.8. And the height is 30 meters. So this 2 minutes, that is just extra information. And we solve. We put that into our handy-dandy calculator. So you just put in 500 times 9.8 times 30, and you get a really big number. 1, 2, 3. And that's joules. Or you can put that into scientific notation. It'll end up being 1.47 times 10 to the 1, 2, 3, 4, 5 joules. So either way, there you go. So number 3, it says, when doing a chin-up, so that's when you have the bar and you pull your chin above the bar, a physics student lifts her body with a force of 24 newtons, a distance of 0.25 meters in 3 seconds. What is the power delivered by the student's bicep? So again, let's write down our givens. So we have the force of 24, let's try that again, 24 newtons. We have the distance being 0.25 meters, and we have the time being 3 seconds. And we are looking for power. Power is always measured in watts. So our equation for power, we only have one, is power equals work divided by time. But we don't have work in our givens. let's see if we can figure out work. Work is just force times distance. Oh, we got force, we got distance. So again, we can just take that, plug that in, and we get that power equals our force times distance over time. We just substitute. We're still looking for power. Our force is 24. Our distance is 0.25 divided by 3 seconds. And then we get our solve to be, plug that into your handy-dandy calculator, 24 times 0.25 divided by 3, and you get the answer to be 2 watts. There you go. So number 4, Reveille always runs in with the Texas A&M football team, except when it's COVID. Girl. Anyway, Reveille's mass is 21.3 kilograms, and she can run about 6.7 meters per second. What is her energy during the run? The run-in. So if it's moving, what type of energy are you dealing with? Hopefully you said kinetic. So let's write our givens out. So our givens, we are given the mass of Reveille to be 21.3 kilograms. And we're also given the velocity of Reveille to be 6.7 meters per second. Our unknown is just energy, but being specific, it is our kinetic energy. We're looking for our kinetic energy. That's always in joules. Our equation that will end up being used is that kinetic energy equals 1/2 mv squared. So then we just substitute in our kinetic energy, that's what we're looking for, equals 1/2. Our mass is 21.3. Our velocity is 6.7 squared. Do not forget about that squared. You don't know how many people have forgotten that squared before. Now you just plug it in. You do 1/2 times 21.3 times 6.7 squared. And you get, so you solve, you get that your kinetic energy equals 478.08 meters. Oh, kinetic energy is in joules. And that's our answer. So it's just asking for her energy. That's very broad, but you know it's either got to be kinetic energy, potential energy. So since it's dealing with movement, you have velocity, you knew it'd be kinetic energy. So Old Rock was getting ready for the game against Alabama. Don't get me started on that one. By lifting weights. The work he was doing was 245 joules with a mass of 45 kilograms. What speed was Old Rock working at? So let's start with our givens. So we have says work, so it gives us work to be 240 joules. It gives us a mass to be 45 kilograms. We always know gravity, right? To be 9.8 meters per second squared. And that's about it. So our unknown, what are we looking for? We are looking for our speed. So we're looking for our v. And we know that needs to be in meters per second. So our equation. So the only equation that does work and velocity is work equaling our change in kinetic energy. So our work would end up equaling 1/2 mv squared. We just substitute. So work equals 245 equaling 1/2. We know the mass to be 45 and v squared. So we didn't need the gravity after all, but it never hurts to write it down. So we can go ahead and do 45 times our 1/2, and that gets us 22.5 velocity squared equaling to 45. We need this 22.5 on the other side, so it's being multiplied. So the opposite of multiply is divide. So I'm going to go ahead and divide that by both sides. And we get that our v squared equals 245 divided by 22.5, which gives us 10.89. We need to get rid of the squared. The opposite of squared is square root. We just square root our answer. And you get that the velocity is about 3.3 meters per second. So he's booking it. So 6, a box pushed at with a net force of 200 newtons at a distance of 9 meters. What is the work done? So again, we're going to write out our givens. So we have force is 200 newtons. We have our distance, which is 9 meters. Our unknown is work, which always measured in joules. So our equation would just be our work equals force times distance equation. We're looking for work. So we can substitute. We have our force, which is 200. We have our distance, which is 9. So our work would just be 200 times 9. And that gives us an 18,000 joules. That was pretty easy. So 7, Jack and Jill went up a hill to get a pail of water. Coming down, the pail was 24 kilograms, and they did 453 kilojoules of work. What is the height of the hill? So we're going to, again, write down our givens. So our givens, in this case, was mass, 34 kilograms. Our work is 453 kilojoules. Hold it. We have an issue. We don't like kilojoules. We need to convert that into joules. So kilo, if we think about exponent-wise, is 3. Joules would be 0. So we're moving 3 to the right. So we're literally going 1, 2, 3. So it would be 4, 5, 3, 0, 0, 0 joules. That's a lot of energy. Whew, that's a lot of energy. And we're looking for the height. So our unknown is height. So our equation we can use is, and don't forget we also have gravity, right? So gravity is 9.8 meters per second squared. We can use work equals force times distance. We don't know our forces, but we do know that force equals mass times acceleration of gravity, because it's specifically the force of gravity, since it's going down. So we can plug in that our work equals our mass times acceleration of gravity times distance. And this specific distance, it's the same thing as our height. So we can go ahead and put y there. Another way of looking at this one, you can see that our work equals the change, that should be a delta, a change in potential energy. So you could also use that. So if we substitute, we get that work equals mass, which is 34, times 9.8, and we're looking for our height, because we have work. Oops, there we go, we have work. Work's that really big number. 0, 0, 0, 3, 5, 4. So that's our substitute. We go ahead and do 34 times 9.8, and we get over here. So we get 4, 5, 3, 0, 0, 0, equaling 333.2 height. It's being multiplied. The opposite of multiply is divide. And what you do to one side, you gotta do the other. So you're going to take that really big number, divide that by 333.2, and you get that the height of the cliff is 1,359.54 meters. No wonder Jack ends up breaking his crown when he rolls down the hill. That's a tall hill. So 8. Miss Rona went to HEB and was pushing a cart with a certain amount of force. She knows her force because she never leaves home without her force meter. And distance. She always carries a meter stick with her too. What could she make her children solve? So think about this. So if we think about givens, so she has her force and she has her distance. So what could they make them solve for? So of course we can make her solve for work because work equals force times distance. And we can also make them solve for, because work equals our change in kinetic energy. So since we have our force times distance, we can find our change in kinetic energy because she's moving. I think that's about it. So work, you can solve for work, and you can solve for your change in kinetic energy. 9. Wile E. Coyote just ran off of a 190-meter cliff. He does what cartoons do and hovers there before he looks down. What is his velocity right before Wile E. Coyote hits the ground? So again, we're going to write out our givens. So we're given the height of the cliff. We're dealing with height, so we know we're going to be dealing with 9.8 meters per second squared. And our unknown is, we want to know the velocity. The velocity is in meters per second. So the equation, this is actually when you do your potential at the top equals your kinetic at the bottom. Because he has 100% potential energy at the top, and then he has 100% kinetic energy at the bottom. So you just be your mass times acceleration of gravity times height equaling your 1/2 mass times v squared. Now it doesn't give us mass, but if you have a mass here and a mass here, your masses actually end up canceling. Because basically what you're doing is you're dividing both sides by m. And you have 1/2 v squared. So now you can do your substitution. You know your AG is 9.8. We know the height is 190. You have 1/2, and you're looking for the v squared. So you'll just take your calculator and do 9.8 times 190, and you get 1,862 equaling 1/2 v squared. You're going to multiply both sides by 2 to make that 1/2 goes away. So you get 3,724 v squared. To get rid of that squared, you're going to square root. And once you square root your answer, you get 61.02 meters per second. And that's how fast he's hitting the ground. That's a lot. No wonder when he hits, he kind of goes into the ground a lot and squishes. So number 10. Oops, didn't mean to do that. It says Pikachu has a very stretchy face. Charmeleon was being mean to Pikachu by stretching his face 0.1 meters. What is the spring constant of Pikachu's face? Now, without this extra information, we're going to say that the elastic potential energy of Pikachu's face, let's say it's 1,000 joules. Okay? So you can't solve for this problem without that extra information. So we do our givens. So you do know that your elastic potential energy is now 1,000, and we know that he stretches, so that's going to be our x, 0.1 meters. Our unknown is our k. So what equation we're going to use is our elastic potential energy equals 1/2 k x squared. If we're plugging in, we know that our kinetic energy, our potential energy is 1,000 equals 1/2 k, and our x is 0.1 squared. So we can go ahead and do 0.1 squared and multiply that by 1/2, and we get that 0.005 k equals 1,000. We're going to divide, so we get k equals 1,000 divided by 0.005. That is a really big number. And there is your spring constant is newtons per meter. There you go. So Miss Heath is playing Super Nintendo Mario's Brothers. She is trying to make Mario run and jump over Bowser while Mario was on a cliff. But her dog jumps in her lap, making Mario hit Bowser. If Mario has a mass of 25 kilograms and was running at a speed of 2.5 meters per second off the cliff at 30 meters, what speed did Mario hit Bowser at 6 meters? So I know a lot of people are having trouble with this one, so we're going to kind of draw it out so we can see it. So Mario's on a cliff. Okay. Mario's on a cliff. We have Bowser here. So what happens is he goes and boing, lands on Bowser. So you have to think about what type of energies is happening up here. What type of energy is happening down here? So up here, we have some type of gravitational energy because he has a height, and we have some type of kinetic energy because he's moving. Same thing down here. We have some type of gravitational because he's on top of Bowser's head, and he's moving, so we have some type of kinetic. So if we're going to do our givens, so our givens, we're given mass of Mario, which is 25 kilograms. We are given the initial speed of Mario, which was 2.5 meters per second. We were given the height of where Mario was, 30 meters, that's our initial height. We know that Mario's final height is 6 meters because he's on top of Bowser's head, and we know that our acceleration due to gravity is 9.8 meters per second squared. And we're looking for our final velocity. Let me rewrite that. That looks really bad. So we're looking for our final velocity. Which is in meters per second. So the equation we just did from our picture. So we're going to do our gravitational potential initial plus our kinetic energy initial equaling our gravitational potential final plus our kinetic energy final. So that gives us mass times acceleration of gravity times height initial plus 1/2 mv initial squared equals MAGY final plus 1/2 mv final squared. A really cool trick is if you divide everything by m, all of the masses cancel out. So you actually don't have to worry about the mass. So you just do acceleration due to gravity times your initial height plus your 1/2 v initial squared equals your AG final height plus your 1/2 v final squared. Then you just plug in what you got. So we have 9.8. Our initial height was 190, and the initial 1/2, that's a horrible 1/2, and the initial was 2.5 squared. And that equals, again, 9.8. Our final height was 6, plus 1/2 v final squared. You can do little individual things. So you can do 190 times 9.8, and you get 1862, plus you do 1/2 times 2.5 squared. That gives you 3.125. You can do 9.8 times 6. That gives you 58.8. And then that can just stay 1/2 the final squared. You can go ahead and add 1,862 plus 3.125. I'm just adding these up. And you get 11865.125 equals 58.8 plus that. We need this on the other side. It's being added. So the opposite of adding is subtracting. So we're going to subtract that by 58.8. You're left with 1806.33 equaling 1/2 the final squared. To get rid of 1/2, we're going to multiply by 2. All of this is just algebra. All of this is just algebra. V squared, get rid of the squared, u square root. So the square root of your answer is just 60.11 meters per second. So he's hitting Bowser pretty hard. There you go. We're almost done. Last one. So we have a chart. So we can figure out our potential energy, our kinetic energy, our mechanical energy, our velocity, and the percentage of the energy and type. So don't forget that your potential energy, gravitational potential energy, is just mass times acceleration of gravity times height. Your kinetic energy equation is 1/2 mv squared. Your mechanical energy equation is your kinetic energy plus your potential energy. Your velocity, you're going to end up using your kinetic energy equation, mv squared, but we need velocity by itself. So that means we're going to go ahead and move the 2 over. So we have 2 kinetic energy equals mass v squared. We divide both sides by m. So we get v squared is 2ke over m. And then just square root both sides. So you get that your velocity is the square root of 2ke over your mass. And the percentage is just saying how much of each type. So yeah, so let's just rock and roll. So let's do our potential energies first. So we're doing all of our potential energies first. So potential energy is mass times acceleration of gravity times height. Our mass is 100. And so this is for number 1. Our mass is 100, acceleration of gravity is 9.8, and the first height was 20. So then you just do 100 times 9.8 times 20. And you get that your potential energy is that big number, joules. 2, same height, so that's for 1 and 2. So for 3, again, you're going to have your potential energy equation equals mass times acceleration due to gravity times height. And the following buses in the following order. So mass is still 100. Acceleration to gravity is 9.8. But this case, our height is 10. So you just plug that in. 1112. And you get that the potential energy is 9,800 joules. And 1158. If students from those buses only will please head out to the fourth part and get on the buses. Again, you're using the exact same equation. That bus has been called. Then we will call in just a few minutes. So we have a mass, 9.8, one more time, the buses are 10 and 0. 0 times anything just gives you 1151, 1011, 0. 1062, 1112, so that's all of your potential energies. 1097. So now let's look at our kinetic energies. And 1158. So our kinetic energy equation is 1/2 mass times b squared. So for the first one, we're looking for our kinetic energy. Again, we know the mass is 100, and we know at the beginning our velocity is 2. We get that from the reading and from there. So our kinetic energy, just plug it, so it'd be 1/2 times 100 times 2 squared. And you get 200 joules. So that's part 1. Now part 2, part 2 is going to be the same because it's the exact. So that's for part 1 and part 2. Part 3, we can't exactly do just quite yet because we don't have the velocity for when it is at part. So we can't do part 3 or part 4 just quite yet. Let's fill in what we got. So we know that this is 19,600. And we know that this is 200. Remember that your mechanical energy, so we're going over mechanical energy, to solve for this is for the first and second, it's the same. Your mechanical energy is just your potential energy plus your kinetic. So if our potential is that and our kinetic is that, our mechanical energy is just, forgot a number. It's just going to be that. Now, remember that what's so special about your mechanical energy, it's all the same. No matter what happens, your mechanical energy is going to be the same. Good afternoon. We'd also like to include the youth center bus. It is also here. So if you are taking the youth center bus, you may head to the bus loop at this time. So this would be the same. It's a 6. That'd be 200. Our 10 was 98, and that was 0. So our third part, we can actually use our mechanical energy equation equals our kinetic plus our potential, because we know that our mechanical energy is that. We don't know our kinetic, but we know our potential is that. So we can just solve for kinetic energy using that equation. And you get, should just be 1,000, or 10,000, sorry. And then you can do the exact same thing for part 4. And then plus your potential energy, your mechanical energy again, is this number here. We don't know our kinetic energy, but our potential energy was 0. So our kinetic energy is just going to be that. So we can plug that in. So this is our, and then our, that's 10,000. So there we go. So we were able to solve for all of the energies. The velocities, like we have our equation here, so if we're looking for velocity, so part 1 and part 2 are already done for us. But part 3, we're going to use velocity equals the square root of 2 kinetic energies over mass. So our kinetic energy for part 3 was about 10,000 over the mass, which is 100. Just plug that to your handy calculator. 2 times 10,000 divided by 100. And you get that your velocity is 14.14 meters per second. So you plug that in there, 14.14 meters per second. And then for part 4, again, you have your velocity is the square root of 2 kinetic energy over mass. Your kinetic energy for part 4 is all of it, so it should be booking it. And you'll just do the square root, 2 times that divided by 100. And you get that your velocity is 3.1.46 meters per second. So it makes sense that the more it goes, the faster it gets, because all of your energy is being converted into kinetic. So it'll be 31.46. So there you go. It is kind of a lengthy problem. So then percentages of the energy. So basically, what's happening here? So here at the top, we have 100%. Oh, that's not a good one to use. We're going to use this one again. So we have 100% potential energy, and not 100%, because it's moving. So we have about, I would say, 75% potential and about 25% kinetic. And that'd be the same for the same, because it's the exact same hill. So potential would be 75%, and kinetic would be about 25%. The second hill, we have for potential energy would probably be about so not quite 20%, but not, so we'll say it's about 30%, and our kinetic energy is about 70%, which makes sense because there's more kinetic energy than there is potential. And then at the bottom, you would have 0 potential and 100% kinetic. So it's just showing you that it's an even transfer. So if you have any questions, make sure you ask Miss Templeton or Miss Heath. Miss Templeton or Miss Verona. Have an awesome day. Remember, you're loved and appreciated. Bye.